Okay, welcome back everyone to the One Word Mind seminar. So today it's my pleasure to introduce you Flavio Dupin Calmon. Hopefully I pronounce it correctly.
Yes.
Um, so he is associate professor of electrical engineering in Harvard. His research basically work on information theory, signal processing, machine learning, and artificial intelligence. His goal is to develop fundamental theory that guides the responsibility design of machine learning and artificial intelligence, for example, in the aspect of reliability, safety, and privacy. And without further ado, I'm really looking for the talk, and the floor is yours.
Yeah. Thank you so much for the invitation and thank you for having me for this talk. And while I'm presenting, if anyone has any questions, feel free to just like unmute yourself or I'll try to be looking at the chat as well. So today I'm going to be talking a little bit about the work that my research group at Harvard has been doing on inference-time information theory. And I'll explain what I mean by that in a bit. And we're going to zoom in into two pieces of work on LLM watermarking. If you don't know what LLM watermarking is, you're in the right place. So this is the outline of the talk. I'm going to start with just a brief outline of what is inference-time information theory. And by that, I mean working on interesting new problems that emerge when we treat LLMs as black boxes, as conditional probability distributions, and what information theory tells us about how to engineer more trustworthy and reliable um, AI systems. And then I'm going to jump into an application which is on LLM watermarking. Hopefully, I'll convince you that this is an interesting area to do research in. Because specifically, if you're interested in coding theory or information theory, this is a place where coding theory and optimal transport meet. And I'm going to talk about two lines of watermarking work that we've done in my group, starting with zero-bit watermarking. And if I have time, I'll give more details on multi-bit watermarking. So I'm going to start with a brief outline. So the question that has been motivating a lot of the research that I've been doing in the past couple of years is how can we build reliable systems using unreliable components? And this question is a question that is as old as information theory and theoretical computer science itself. In fact, this is a question that von Neumann asked back in the early days of computing in the 40s. Back at the time, von Neumann, generational talent, mathematician, he saw these new machines emerging, right, being built in the United States and the UK, which were computers. And in fact, as a mathematician, he was really drawn to these new powerful devices. And he joined the conversation of one specific computer, the EDVAC, around 1944. And in fact, he wrote the first draft of a report on the EDVAC, which is known as one of the most important drafts in computer science, where he introduced the von Neumann architecture, which is the way that we design CPUs today. And back in that time, one challenge that von Neumann faced is that these computers were highly unreliable. In fact, in his report, he writes that malfunctioning of any device has a finite probability of error, and any error may vitiate the entire output of the device. However, it may be possible to avoid even these phenomena to some extent. So we had these powerful new devices, these computers, but they would fail quite frequently. In fact, at the time, the amount of time you could run a computer reliably without some valve blowing or some kind of mechanical component failure was about 8 hours. And at the time, von Neumann was thinking a lot about these problems and basically thinking, how can we make these computers more reliable so we can use them for longer to have more reliable and consistent computations? And in fact, a few years later, he gave a series of lectures at Caltech on probabilistic logics and the synthesis of reliable organisms from unreliable components, where he describes how you can add redundancy to these new devices in order to perform reliable computation, even though these individual components may fail. So this question of reliable computation over unreliable devices had is something that dates back to the origins of computer science and information theory as well. In fact, this series of lectures by von Neumann was actually transcribed and published on a volume that was edited by Claude Shannon, who was also seeing these computers emerging and dealing with their unreliability. He actually wrote a paper with more on this, on reliable circuits using less reliable relays, where he presents several of the ideas of like trying to add redundancy to computations in order to add more reliability to these computers. So over the next decades, the way we design computers became much more reliable. And in fact, today we don't even think about this, right? If you look at our processors that we build are extremely complex, right? This is just one die shot of one microprocessor. It's an extremely complex device. And we can run these computers for hours on end without expecting significant failures, right? And in fact, I can even write a piece of code in, say, NumPy, and compile it to an ARM processor, an AMD processor, an Intel processor, and I expect to have about the same computation across these different devices. So over the next decades, commercial-grade computers became much more reliable. But now we have the emergence of a new computing platform, right? Which are these large language models. So these models that are inherently stochastic. What they do is that their outputs are in fact a probability distribution. If you send a query to ChatGPT or to Claude or to Gemini, the output of the model is the probability of the next token, right? Which next token, next little piece of word is the most likely to follow the input. And now we're trying to build incredibly complex systems over these large language models. And the same question it becomes relevant again. How can we build reliable systems using these unreliable components, these AI systems that are inherently stochastic, where if you send the same prompt even to the same model twice and you just change the seed which you sample the output from, you're going to get a completely different answer. And these systems have become increasingly more reliable, right? This is one example of data on this. This is called the meter benchmark, where you computed the time horizon that it takes for an LLM to accomplish a complex task, like train a classifier and so on. But if you look at where we are now, we are about where von Neumann saw computing back in the 1950s. So we can run these models for about 8 hours on end to try to do some complex tasks. But after that, we have issues of hallucinations, of managing context windows and compressing caches and things like that. And another challenge we have here is that our notion of reliability is not just reliability in the computations of these systems, right? These systems, they are embedded in society, right? They include biases and information that exists in the data that was trained that was used to train them. And they can also be used to create fake news, to influence discourse. It's used in several different ways by different people, all the way from health advice to education and learning. So when we talk about reliability in these systems, we want them not only to be consistent, but also to be trustworthy, interpretable, preserve privacy, and should not cause harm. So this question of how can we build reliable systems using these unreliable and inherently stochastic AI models is something that my group has been thinking for the past couple of years, trying to understand issues of alignment and reward hacking, trying to interpret the hidden activations and what's actually happening inside these models. And what I'm going to do today is that I'm going to focus on one specific problem on reliable AI, which is the problem of auditing, which is the problem of LLM watermarking, inserting a signal into the output of this model so we can detect if the text that was generated by it was AI, the text that it outputs is AI generated or not. So for the rest of the talk, we're going to zoom into this piece of LLM watermarking. And I'm going to start talking about one type of watermarking known as zero-bit watermarking, where we just want to detect if the text is AI generated or not. So this is what I'm going to talk about next. And for the next about 20 minutes, I'll be focusing on one piece of work that we presented at NeurIPS last year called HeavyWater and SimplexWater, watermarking low entropy text distributions. And this was joint work with Dor, who at the time was a visiting student here at Harvard, Carol, Claudio, Sean, and Richard at JP Morgan Chase, Haim, and Sajeni, who is a postdoc here at Harvard. So we will be talking about adding watermarks and signals in the output of a large language model. But why watermark? Why would we want to do this? So large language models demonstrate human-level abilities to generate text. And because of that, that can be prone to misuse. LLMs can be used to generate misinformation and fake news. AI-generated scams can be used for plagiarism and academic dishonesty. One main motivation for us, and in fact was one of the big motivators behind this research that was done together with our collaborators at JP Morgan Chase, is regulations. There are several regulations that are calling for LLM outputs to be watermarked, to contain this watermark. And specifically, watermarking adds a layer of transparency and auditability to the output of a large language model. So you can see if text that's being generated inside your company was actually generated by your models or not. So the question that we ask is, how can we reliably embed and detect watermarks in large language models? And the key idea is to skew or change or bias the next token distribution. So we add a watermark not by changing the tokens that are produced by a model, but by changing the distribution from which these tokens, from which these outputs are sampled from. And over the past few years, this area has really seen a flurry of work dating back to the work by Kirschenbauer et al. And several others that I'll be discussing as we go along. But the first thing I want to do before I talk about our exact LLM watermarking scheme, I just want to give you a simple cartoon, a simple toy example to motivate the problem. So instead of looking at watermarking large language models, we will be looking at a simpler problem that is watermarking dice rolls. And this is a similar problem to what we're going to be looking later, but this is just to kind of motivate the main mathematical mechanics and modeling assumptions that exists behind this problem of LLM watermarking. So let's forget large language models for now. Let's assume that we want to watermark a dice. So we have two dice, one that is watermarked in red and one that is not watermarked. And the game that we're going to play is the following. We're going to flip a coin, an unbiased coin, and probably 1/2, you're going to choose the watermarked one, 1/2 the not watermarked one. And we're going to sample n samples from this dice. We're going to roll it n times. And a watermark detector will observe the dice rolls. They will not have access to the dice. They only observe the dice rolls. And they're going to have to make a decision. Did these dice rolls come from the watermark dice, from the red dice, or did it come from the green dice, the one that's not watermarked? So how could we build a watermark for these dice rolls? So if you think about this problem for a little bit, maybe the first thing that would come to mind is that, well, I'm going to change the source distribution. And what I mean by that is that I'm going to change and bias the dice that I want to watermark. I'm going to make it or change its shape or its size to make it different from the one that's not watermarked. Mathematically, the way we can model this is that assume that we have a function that maps the dice sides 1 to 6, 1 to 0, and 1. And instead of having a uniform dice, what we're going to do is that we're going to slightly change the probabilities of these dice roll according to a function f that we are going to call a score function. So for example, in this case, the score function is 1 if the output is 1, 2, or 3, 0 otherwise. And what this means is that we're going to slightly increase the likelihood in this dice that we observe 1, 2, and 3, right? So we're going to bias this. So so what we can do is that if we roll the dice, our watermarker can detect the dice rolls. And if the score is different from 1/2, it's going to declare that the output is watermarked. If not, it's not watermarked. But the problem here is that the dice roll is distorted, right? Now our watermarked die is no longer a fair dice. So what we can do in order to try to watermark the dice without changing its probability distribution, is that we can share site information between the watermarker and the watermark detector and use shared site information in order to couple the site information distribution and the distribution of the dice P of X, so that the average next token distribution, in this case, the average dice roll distribution, doesn't change. But it makes it easier for the watermarker to detect if the dice is watermarked or not. Let me explain a little bit more what I mean by that. So assume, for example, just for the sake of example, that we have some shared site information between the watermarker and the watermark detector, and that this site information is, say, a sequence of unbiased coin flips, 1 and 0. So what the watermarker can do in this case is that they can create another score function. Now this score function depends on the outcome of your dice, 1 to 6, and the site information 0 and 1. And let's say we define a score function that looks something like this. And now when the watermarker is going to roll the dice, they're going to roll it using in terms of using a coupling, P of X of S, that's found by maximizing this score function. And the solution here is this, the coupling for this score function, the one that maximizes the score, is this one here. So if your site information is 0, you're going to roll the dice, only choose uniformly between 1, 2, and 3. And if it's 1, you're going to choose uniformly between 4, 5, and 6, right? So the interesting thing here is that the marginal distribution of the dice is still uniform, right? If you take the average over S, as long as S is an unbiased bit, you're still picking uniformly between 1 and 6. So you didn't distort the dice roll on average, but a watermarker who has access to the site information can detect if the dice roll was watermarked or not. And just to drive this point home, when the watermarker is going to draw the next dice roll, they're going to observe the piece of site information and sample according to this coupling, right? And for example, if the watermarker has 2 samples, sample A and sample B, they can try to guess which one is watermarked. Since I'm on Zoom, I'm not going to, I'm not sure if I'm going to risk asking someone if they know which dice is watermarked or not. So I'm just going to give the solution. But if you were to look here, you would say like, well, for sample A, I have 0 and 1. That's a feasible outcome here. For the second sample, I observe 1 and 4. That's a feasible outcome here, and so on. So this could be watermarked. And for sample B, you can see that immediately I observe 0 and 5 here, which is not an outcome that's allowable by our coupling. So I immediately know that this second sample cannot have been generated by our watermark. So there are 3 key ideas that were involved in watermarking this dice roll. The first one was that we had a watermarker who observes the dice rolls, who knows the distribution of the dice. In the LLM context, which we're going to be switching to now, this means that the watermarker has access to this next token distribution P of X. And they have a score function that they agreed with the watermark detector. And they're going to solve this optimal transfer problem. They're going to find a coupling that maximizes the score. And they're going to sample according to the solution of this optimal transfer problem. So they're going to produce a token in the LLM case, in the dice roll case, a dice roll based on this conditional distribution. And the watermarker, knowing the score function, they're just going to try to detect the watermark directly from the site information and the tokens without access to the model. And they're going to compute this average score and make a decision if the sequence of observations that they had was watermarked or not. Yeah. So,
Question, Flavio?
oh yeah. Hey, Anand. Hi.
Nice to see
Hey.
you. So there's no adversary, I guess, right now in this picture, but
Yeah.
is it assumed that the score function is public?
Yeah.
Okay. Just
So 2 things, like, so we assume that the score function is public and known by the watermarker and the watermark detector.
mm-hmm.
And yeah, and the site information is shared between the 2 of them. Yeah.
Okay.
So no adversaries here, no one, and I want to be cautious with my words. I'm not saying we're trying to hide the secret or anything like that. We're just trying to
Yeah, but somebody
watermark
might not
the.
have forge. I guess my thought was somebody
Yeah,
might want to
exactly. I'm not
forge. So,
considering the forging setting if you're going to
oh, you
forge a
aren't. Okay,
watermark,
okay.
something like that.
Then
Yeah,
maybe I
not
didn't see
yet
it.
at least. Great. Awesome. If there are no other questions, so just to recap, there are three ingredients that we needed to watermark this probabilistic source. The first one was shared site information between the watermarker and the watermark detector. The second is a score function that will tell me how I'm going to design this coupling between in the LLM setting the next token distribution, in the dice roll setting the dice roll, and the information that the detector had. And the third one is actually solving and finding this coupling. So for the shared site information, in practice, the way we do this is that we create this site information by hashing previous tokens in a shared key between the watermarker and the watermark detector. So the goal is to design a watermark that only depends on the text that you observed. And in this case, we can extract this site information by hashing previous tokens. That adds dependency and makes also the watermark less robust to token changes. But for now, just for the purpose of our theoretical analysis, I'm going to abstract that away. And we will just assume that the site information or IID random variable is drawn uniformly from a distribution between 1 and k, and 1 and k. So between k integers. So we, again, like this adds dependencies, and that also makes the watermark less robust. But this is a common assumption that's done and implementation that's done in most watermarks that I'm aware of. And for our mathematical analysis, we're going to assume the site information is IID. And I want to quickly mention this third component here, like this coupling, given that the watermarker has access to the probability distribution of the source. In the LLM world, what that means is that the watermarker has access to the next token distributions. They can solve this optimal transport problem, given that the score function is known and public. And that adds very little overhead in generation, because usually these are small these are small optimizations compared to like generating the actual next token. And our focus will be
Interesting.
on the
Actually,
second point
sorry.
here. Yeah, go ahead.
Another question about that, right? I don't know. I was just talking to my student earlier today, and there were like 8,192 possible tokens in
Yeah,
that particular example. So this is optimization over you're not perturbing the tokens, right? So it's
yeah,
the
yeah. So
hash,
that's a
right?
great point.
Okay.
So the token vocabulary for like even some models are like 200,000 tokens.
Right, yeah.
One point that I'm going to make in a little bit, that's an excellent point. And so there are two simplifying assumptions that we make. First is we consider top K and top P tokens, which means
Mm-hmm.
that we only sample from tokens that accumulate up to like 95 or 99% of the
Mm-hmm.
probabilities, and usually restricted to the top K tokens, which is 20 and 30.
Okay.
I'll show a graph in a little bit that shows that the vast majority of next token distributions have
It's highly
mass in at
concentrated.
most like
Yeah.
50 tokens or 60
Okay.
tokens. And the
Cool.
reason is the soft max
Right.
layer at the output that really makes like most tokens have probability
Negligible.
like
Right.
below 10 to the minus 5 or minus
Right.
6.
Okay, cool. Thank you.
Great, awesome. Any other questions? Cool. So again, these are the ingredients. We need this site information. We need to compute this coupling. And the question is like, what score function should we use, right? So if you buy this model, what remains is how do we design this score function for watermark detection? So this is what I'm going to talk about next. How do we design this score function? And our goal will be to maximize the average score difference between watermarked and unwatermarked tokens, right? So remember that under our constraint on the watermark detector, they're going to compute this average score between the observed tokens and the site information. And the goal is to increase the difference between this average score, this gap that we call D gap, when tokens are generated by the non-watermarked distribution, which means when your site information and your next token distribution are independent, versus when they're coupled, when they're solved using the coupling produced by the watermarker. Now, the challenge here is that we're assuming that the watermarker doesn't have access to the model. They're going to try to detect the watermark directly from the tokens and from the site information. So they don't know what actually is P of X. What is this next token prediction? The watermarker knows, but not the watermark detector. So the challenge here is that this score function cannot depend on P of X, right? Because the next token distribution changes at every given time. So in order to solve this optimization problem, we're going to minimize here for the worst case distribution. So we're going to assume that the distribution comes from a set, and we're going to consider the worst case distribution. And specifically, the set that we're going to assume are distributions that have a given have very low min entropy. What you're seeing here is a plot that we measured from, I think, a Llama model, where on the x-axis, you have the percentage of tokens that have on the y-axis, you have the percentage of tokens across multiple generations in coding and question answering tasks. And the x-axis, you have the infinity norm of the next token distribution, so the max probability. And you can see that the majority of tokens, over 95% of the tokens, have at least have next token predictions, where at least one token has probability 0.85, right? So this goes back to the question that Anand had, like our distributions have very low min entropy. So that means that at least one token is very likely to be drawn up from. And that kind of makes sense. If you think about language, after the token the, probably a space will come. And, so it can be very deterministic. So we're going to be designing our score function we're looking at the worst case design over all distributions whose most likely token is below a given value, lambda. So in this case, we want to design a score function that maximizes this worst case score gap. And we're going to be restricting our search for now. We're going to relax that later to optimize over binary score functions. So we're looking at score functions that get a token and a piece of site information and maps it to 0 or 1. So this is the optimization problem that we're faced with, where we want to maximize this detection gap, where the detection gap depends on the cardinality of site information k, the number of tokens that you have in your vocabulary n, where lambda is your min entropy constraint, and cal of f is this family of score functions that we're optimizing for, which for now we're going to assume is binary. So this is the optimization problem. So the first thing, if you stare at this for a while, the first thing that you'll notice is that this inner minimization here, since we're minimizing this concave function, that the minimizing distribution will be on the facet of the simplex. And if we consider this min entropy constraint to be 1/2, meaning that in your next token prediction, at least one token has probability at least 1/2. So that happens the vast majority of the time. The worst case P of X will be on the facet of the simplex, and it will be of this following form. So it will assign non-zero probability, lambda and 1 minus lambda, to only 2 entries, right? So your worst case kind of next token distribution under this constraint is one that assigns lambda to one token and 1 minus lambda to another token. And the implication of this is that if you were to write your score function as a table, right, on the x-axis you have your token vocabulary from 1 to m. On the rows, and on the columns you have your site information cardinality. And again, we're assuming binary score functions, so they're 0 or 1. Your performance will depend on the minimum distance of pairs of rows, right? Because that's what's going to dictate the performance under these worst case distributions P of X. So performance depends on the minimum distance between pairs of rows, just like a channel code. And you can actually make this claim very precise. And it's stated here in this proposition that if you consider functions that are binary, score functions that are binary, and you consider this like the rows of that table, then your gap will depend on the Hamming distance, the minimum Hamming distance between pairs of rows of this table, where it also depends on your min entropy constraint here and your cardinality k of your site information. And the takeaway here is that generating score functions that give this large separation between detected scores is equivalent to designing code books with large Hamming distance between code words, which is a traditional and a classic problem in coding theory, which is well understood. And then specifically, this can give us upper bound on the maximum gap on the performance of our watermark under this assumption of score-based decoding, where you can see that this maximum gap is upper bounded by m1 minus lambda over 2m minus 1. And the point I want to make here is that this is a direct application of the Plotkin bound, right? That gives you a bound on the Hamming distance between two code words. And the design implication of this is that designing the score function using that if you want to design a good watermark, you want to design you want to use a score function that's based on a code book that approximates the Plotkin bound in terms of Hamming distance between pairs of rows. And there are known code constructions that do that. One of them is the simplex code, which is the code that we used in our first watermark design that we call SimplexWater. SimplexWater because of simplex codes. And just to bring all of this together, so the watermarking process is what I mentioned in the beginning, where we have a watermarker that observes the next token distribution and computes a score maximizing coupling. Then we'll sample from that next token distribution, and your detector will compute this average score and detect if the text is watermarked or not. And the key difference here is that this binary, that this score function is generated using a simplex code, right? Because of this equivalence between optimizing over binary score functions and designing a code book with large Hamming distance between pairs of code words. So let's see how that performs in practice. So we're going to do this watermarking process with the F chosen from a simplex code. So what I'm going to show here is performance of watermarking, where the model we're considering is Llama 7B, and the task is financial Q&A, is question and answering about finance. This is a standard data set for LLM evaluation. On the x-axis, I have distortion, so cross-entropy relative to the unwatermarked text. And on the y-axis, I have detection of the watermark for log p, and p is the p-value in detection. You can see if I have no watermark on my text, then I achieve the minimum cross-entropy. And in this case, your detection probability is half. You don't know, like you're equally likely to declare the text as watermarked or not. So we can look at competing watermarks. One is by Kirschenbauer et al. This is known as the red-green watermark, and this is very similar to the first construction for the dice that I mentioned in the beginning of the talk, where we bias the die a little bit, making the one side or another side more or less likely. This has a similar construction where we distort the text so that it's not zero distortion, but we make certain tokens more likely than others. There's also a collection of low distortion or no distortion, distortion-free watermarks. These are watermarks that preserve the marginal distribution of the next token prediction, so they're distortion-free like our construction. So here we have one based on inverse transform. This one is a previous work that we presented at ISIT last year, and the green one is SynthID introduced by Google. And this is the performance of SimplexWater. You can see that it achieves a better trade-off between distortion and detection. I didn't really mention how we get this distortion. We do this by just tilting the probability distribution, but you can see that Pareto dominates these competing methods. But when we did this plot, we were pretty excited, but there was one watermark that was missing. And this is a watermark that was introduced by Scott Aronson and other folks at OpenAI, where it's based on, we call it the Gumbo watermark. It's based on using Gumbo distributions. And you can see that here it performs slightly better than SimplexWater. So it achieves a higher detection level at the same no distortion region. So there's a gap here. And sure, we can distort our watermark and outperform it in terms of detection, but we were quite puzzled when we saw this. So we went back to the drawing board and asked, how can we improve our design? And if you look at our original formulation, one big restriction that we impose here is that our watermark score is binary, right? So we're getting the score function to be 0 or 1. But this is not necessarily optimal, right? So if you're not going to use a binary score function to design this, which function should we construct? So like most information theorists, the first thing that comes to mind is to use a random score, right? Is to generate a random codebook. In this case, where each entry here is sampled IID from some distribution, P of F, where P of F denotes the score distribution that you're sampling from. So in this case, your gap will be a random variable itself, right? Because it'll depend on which distribution you choose. That will change the expected gap that you get. But we can actually understand pretty well what this gap will be. And the claim here is that with very high probability, if you sample from a heavy-tailed distribution, the gap, the detection gap between the scores of the unwatermarked and watermarked text will depend on this integral of the tail of the inverse quantile function of the score that you're sampling from. So what this suggests is that a better design is to just sample randomly your score function from a heavy-tailed distribution, because that's what's going to, in this random case, is going to control the gap. And the heavier the tail, potentially the higher this gap is. And this led to another construction known as HeavyWater, where these scores are sampled from a log normal distribution at random, right? So we still keep the whole process the same, but we just change the way the score function is generated. And when we evaluate this in practice, it performs really well. It actually achieves a higher detection and better distortion trade-off than SimplexWater. And to the best of our knowledge, this is the state of the art within this framework of watermark detection. Okay, so this was our first foray into watermarking. And the question that we asked next is, why stop at 1 bit, right? And this leads to the next and last part of the talk, which is on multi-bit watermarking, and specifically the capacity of this watermarking channel. So the question we ask is, why should we stop at 1 bit, right? Up to now, we've been designing watermarks where we just try to detect from the tokens that we receive if the text is generated by a given LLM or not. But you can imagine squeezing more bits of metadata into the text that was generated, right? Like kind of like a mock-up, this is just a cartoon example, would be that you select text and you can see what model was generated it, when was it generated, potentially which user was responsible for the request that generated that model. So this is based on, so the results I'm going to talk next, this is based on work done with my wonderful collaborators, Atafe, Carol Sajani, and Oliver and Lalitha at ASU. And I'm going to be talking about one construction of such a multi-bit watermark that we call ArcMark. So let me talk about multi-bit watermarking next. I'm going to change notation a little bit just to be more appropriate for this capacity setting. So I'm going to reintroduce the notation here, but it's pretty much the same setting that we have before. So we have a large language model that outputs a next token distribution based on previous tokens. This next token distribution is denoted by Q of T. And we have a watermarker that's going to observe this next token distribution. But now instead of just biasing it to decide if to indicate if the text is watermarked or not, they want to transmit a message over k bits. And based on the message that they're transmitting and the next token distribution, they're going to sample and change the way the next token is sampled from. So there are two things that make this watermarking setting unique. The first one is that, oh yeah, one more thing, and the decoder will then observe the sequence of tokens and will make a decision if the text is watermarked or not. And one thing that makes the setting slightly different than your vanilla communication setting is that here the watermarker has and the LLM have instantaneous feedback because they know which token was generated, so they know if the string of tokens is not changed, exactly what the decoder will observe. And we assume also that we have a shared secret that's shared between the watermarker and the detector and the decoder, who now will decode the message. That, again, this, as in the previous case, is generated using hash of keys and previous tokens. So our goal is to understand what is the capacity of this channel, right? And one thing that makes it different is that we have to assume a probability distribution over next token distributions. So probability distribution over probability distributions, because again, this next token distribution changes over time, right? This is something that's given by the LLM and it changes. We're also going to assume, just like we did in the last section, that we have a distortion-free requirement where we want that on average over the shared secret, that the next token you're always sampling from the same next token distribution. So on average, there's no change to the text. As I mentioned, since the next token distribution changes over time, we need to assume a probability distribution over these next token distributions. So I'm going to assume that next token distributions are drawn IID. So again, I'm not assuming that the tokens are IID, but the distribution from which these tokens are sampled from changes from are drawn IID from a distribution over distributions. This is, of course, a huge simplifying assumption. We're going to use this just for our capacity calculations. But of course, LLMs generate autoregressively, so that will not hold. And we're also going to assume that the token distributions are known causally and only at the watermarker. So just like the previous case, the watermark decoder, the message decoder, does not know what the next token distribution is. And here we can define the usual Shannon-like definition of capacity as the maximum achievable rate in terms of bits per token with arbitrarily small probability of error, asymptotically as the number of tokens goes to infinity. So there are a lot of closely related capacity definitions in the literature, and we build on this work. So specifically, this setting is very similar to channel coding with causal state information at the encoder. That was analyzed by Shannon in 1958, because in this case, the encoder has causal state information because they know what the next token was. And this was the main tool in our capacity proof. The proof is pretty standard in information theory. So I'm just going to give the capacity expression here, and surprisingly, it single letterizes. So given an LLM with next token distributions Q of xt, drawn IID from a distribution over these next token distributions P of Q, the capacity has this single letter expression here, where you maximize mutual information subject to this distortion-free constraint on the marginal distributions. And here we optimize over auxiliary random variables that represent the encoding of the site information in the message M. So I just want to give you one very simple example of capacity calculation. In this case, how can we actually calculate this expression? So we're going to assume that we have a token alphabet from 1 to n. And again, we have to assume a distribution over next token distributions. So we're going to assume that the LLM distribution is always uniform over 2 tokens. So it's going to be 1/2 for one token and 1/2 for another token. And the way these tokens are decided is that you randomly pick 2 token positions that are different, and then you assign them probability 1/2. So that's kind of the distribution where next token distributions come from. And in this case, we have a closed form expression for capacity that in the limit that the token alphabet goes to infinity is about 0.27 bits per token. How can you achieve this? Well, you can have very simple constructions. For example, for n equals 4, we're in a world where we only have 4 tokens, and we still have the same process where 2 tokens are picked uniformly at random and assigned probability 1/2. Then you can compute this capacity expression by choosing U to be binary, uniformly distributed by small and big, and your next token distribution X will be uniformly chosen depending on U across Q. Okay. So we can actually generalize this construction, and we can actually extend this to develop watermarks that we can test on real LLMs. And the idea here is that we're going to do a construction that kind of looks like this simple one that's on the slide here, where we're going to use site information to couple it with the next token distribution, next token X. And we're going to do that on the circle. So let me give you an example of how this construction looks like. And this is known as, this is what we call arcmark. So what we're going to do is that we're going to assign each token an equally spaced point around the circle. And we're going to assume that we have our auxiliary random variable in the capacity calculation U that is uniformly distributed around the circle. And given U, right, our site information and the capacity, we're going to, we will choose the token X that's closest to our site information in arc distance, right? So given U, if we have two tokens, we're going to choose the one that's closest in arc distance. And we can show that this achieves the capacity for binary token distributions and inspires our practical scheme called arcmark. So let me just show how arcmark works with actual LLM distributions. So we have our circle, and we're going to assign each token a point uniformly spaced on this token. And we're going to have p spots that will correspond to the code word symbol that we want to transmit at a given time. And the way the watermarking process works is the following. Given a message M, we're going to use a PRE linear code. In our experiments, we just use a random code, but I'm sure better constructions exist. This will define the code word symbol, the message symbol that we're transmitting. In this example here, it's U1, U2, U3, or U4. And the symbol that we transmit at time t is going to be mixed with our site information, which is also drawn from these p-values of the code word symbols. And we're going to compute the sum of those two. So z here, which is which is going to try to be detected by the watermark detector, is uniformly distributed. And now given z of t, we're going to pick our token x of t, and we're going to couple it with the distribution of z in order to minimize this arc distance between x and z. Again, z will be uniform, x will be given by the LLM, the next token distribution, and we're going to couple them in order to minimize this arc distance here. And again, this is distortion-free because we keep the marginal distribution of x. And how do we decode this? In order to decode, the watermark detector just reverses the operation. So given a sequence of tokens x1 and x2xn and sequence s1 and sn, it just computes the message m that minimizes the distance, the arc distance between x and the site information symbols and the site information plus the message symbol m here. So the way we implement this in practice for now is just exhaustive decoding. We just we declare the code word that minimizes this distance. And the main result here is that arcmark sometimes achieves capacity, not in general, but we can show that for that distribution that I showed earlier for a binary token distribution, arcmark achieves capacity with a slightly modified decoder than the minimum distance decoder that I showed, but it's essentially the same spirit. So here are some preliminary results. We're comparing here against two other watermarks, BIMARK and MPAC. Here on the x-axis, you have message accuracy. On the y-axis, you have number of tokens used for decoding. The model that we use is Llama 3.8b, and here the task is on news and information retrieval. And with 3 bits, we can have a higher message decoding accuracy for the same token length than the competing methods. And we observe a similar trend when we're trying to embed 8-bit messages. We see a dip in performance when we go to 16-bit messages, but performance, it seems that we can more reliably detect more bits at the same token length compared to existing methods. So there's still much more work to be done. This is just our first foray into understanding the capacity of the watermarking channel for LLMs. I think there's a lot of interesting questions in even evaluating the capacity expression for more interesting probability distributions. The value I showed you is when we choose 2 tokens that uniformly at random. It would be nice to understand this for distributions that look more like distributions generated by LLMs. Could we even numerically approximate or understand the capacity of real LLMs? As far as I can tell, it seems to be pretty low, but it would be nice to have a better approximation of that. I can tell you one thing, our watermarks are not robust to text substitution and deletion. What we observed is that this is a property of most multi-bit watermarks, that if you change a few tokens, the detection accuracy goes down by a lot. And arcmark is only one construction. We use this kind of circle-like construction inspired by capacity calculations for this idealized setting where our next token distributions are supported only 2 tokens, but I'm sure other code constructions exist. So I'll wrap up here. So this is just a flavor of some of the work that my group has been doing. We've been exploring other aspects of inference-time information theory. Again, what I mean by that is using these models as black boxes and operating on their probability distributions. We've been looking at aspects like alignment and reward hacking, and also interpretability and explainability. And I just want to finish returning to the question that I asked in the beginning. How can we build reliable systems using unreliable components? And I do think a lot of us feel like probably Shannon and von Neumann felt back in the 50s. We have these amazing new compute architectures. We have these amazing LLMs that are clearly capable of doing very powerful things that go all the way from writing code to math to new, more agentic settings. But there's a question of how do we scaffold them, and how do we reason about the design of these systems rigorously in order to increase their reliability? And by reliability, I mean not only accurate operation, but things like trustworthiness, transparency, accountability, make sure that they ensure privacy, and things of that nature. And I think information theory is really key. This rigorous way of thinking about these problems and boiling the problem down to its underlying probability distributions is key for reliable AI. Thanks. I'll stop here and take any questions.